Okay, more circuits questions. We got figure 4.1 shows part of a circuit where three resistors are connected together. So 6 ohms, 4 ohms in parallel, 5.6 ohms then added in series. The current in the 4 ohm resistor is 0.3 amps, right? So everything, this is all in the picture, so we don't need any of that. Explain why the current in the 6 ohm resistor is 0.2 amps, right? So we've got an explain, so we have to put a little bit of few words together here. So we want to say that the potential difference across resistors in parallel is the same. Across resistors in parallel is the same. So therefore we can say that 4 times 0.3 has got to be equal to 6 times 0.2. They're both giving us 1.2 for the potential difference. That's what we need on that. Part B, state the law which enables you to calculate the current in the 5.6 ohm resistor. So here we're going to be combining our two currents here because we just said that's 0.2 amps. So if we're combining these two at a junction, this is going to be Kirchhoff's first law. Kirchhoff's first law. I think if you can't remember whether it's first law or second law, then you can just write out what the wording of the law saying that the charge flowing into a junction in the circuit is the same as the charge flowing out of the junction. So, but usually people can remember which way round the two laws are for Kirchhoff. Calculate the current in the 5.6 ohm resistor. Right, okay, well that's easy enough. We just add in 0.2 and 0.3 to get 0.5. So far so good. Calculate the total resistance of the combination of resistors. Right, so we've got to add these two in parallel and then add the one on in series. So we're going to want to get all of this over 12. That's going to be our common denominator. So for the ones in parallel, we're going to have 3 over 12 plus 2 over 12 to the minus 1. And then we're going to have to add on the 5.6 for the one in series. So that's going to be 12 over 5. So 2.4 add on 5.6 gives us 8 ohms. Easy enough. To cause the current of 0.3 amps in the 4 ohm resistor, the resistor combination is connected to a DC supply of EMF 5 volts. Explain the term EMF. Okay, so EMF is the, again, we're talking about voltage here. So when, a good way to start, as soon as we've got voltage appears, put in energy per unit charge, because that's what our voltage is. It's our joules per coulomb. So this is the energy per unit charge, just saying what a volt is. Then we're transferring energy from one place to another. So if we're talking about EMF, we're transferring energy. Oh no, energy per unit charge transferred. Let's get that. I'm saying transferring, but I wanted to write down transferred. So if we're talking EMF, we're transferring from the source to the electrical energy. Because if we're talking about PD, we're transferring from the electrical energy to the component that's got the PD across it. But in this case, this is energy per unit charge transferred from the source to electrical energy. So that's really the only difference when we're doing the definition of EMF versus the definition of PD. We're still talking about energy per unit charge in both cases because they're both voltages, but it's where we're transferring from and to. EMF transferred from source to electrical energy, PD transferred from electrical energy to component. So same thing, we're just one's going in and one's going out. Show that the terminal potential difference across the supply is 4 volts. Right, well, we know we've got 8 ohms in the circuit and we know what the total current is. So if we do our V equals IR, then we can say that our V is going to be equal to 8 for the resistance multiplied by 0.5 for our current, which gives us a voltage of 4 volts. So that's all good. Calculate the internal resistance of the supply. So we know then that we're getting 1 volt across the internal resistance because that's the one that's missing. We've got 5 EMF and we've got 4 terminal PD. then we've got 1 volt across the internal resistance, and we know that we've got 0.5 amps going through our power supply, and that's got to be multiplied by the internal resistance. So our internal resistance has got to be equal to 2 ohms. All right, it's a nice warmer upper on circuits. So what have we got next? We've got, all right, it's another one of these ones where they give us some electrical quantities and we just match them up to the units. So electromotive force, this is our input voltage. We know that voltage is joules per coulomb. That's pretty foundational when it comes to dealing with circuits, so that's an easy starter. Resistance, right, well, from our V equals IR, we know that resistance is voltage divided by current, so that's our voltage divided by current there, volts per amp. Energy, there's loads of ways we can write out energy, but we only have to look at these 2 that are remaining now. We've already said that voltage is joules per coulomb, so if we multiply voltage by coulombs, we're left with the joules. So is charge amps second? Well, it is. We know that amps, our current, is our rate of flow of charge. So if we take current and multiply it by time, we're going to get charge. So a nice symmetrical pattern they've given us there. That's the first bit. Part B. Circuit below consists of a cell and 5 resistors. Okay, we've also got some internal resistance. The cell's got 1.2 volt EMF. That's in the picture. Internal resistance, little r. Current at point X is 0.16 amps, right? So that's not in the picture, so I'll highlight that. Define potential difference, right? Excellent. This follows on from our definition of EMF in the previous question. Now, we're more or less going to be writing out the same structure of sentence, but something which is useful both in this definition and a lot of other definitions is contextualizing the term that you're defining. You know, potential differences don't just float around in nothing on their own. They're attached to, you know, a circuit. So let's contextualize it by saying, first of all, the potential difference across a component, because that's where potential difference actually exists. Now, we didn't have to bother saying that for the EMF because we know that EMFs are associated with our power source. Although I suppose, I mean, we probably did say it in the definition. Actually, you know, the EMF of a battery or a cell, you could put that in there, but you don't really need to, as much as we do here with the potential difference. So it sets it up nicely because we can then use some of these words later on in the definition. So contextualize is very good for these definition questions. So the PD across a component, then we can go into more or less the same as we had for EMF. So it is the energy per unit charge, because remember we're dealing with voltage, so that's our joules per coulomb. Energy per unit charge transferred, and now, so we have to say where it's being transferred from and to. So we're going from electrical energy, and now we get the payoff of having contextualized our PD at the beginning by saying to the component. So it all fits together nicely. Right, so that's that one. Now we have to explain what is meant by internal resistance. Right, okay, so this one's got an element of how long's a piece of string. We're talking about internal resistance. But first of all, let's do that contextualized approach. So we can say, well, the internal, I'm going to do some of this in shorthand, obviously write it out in full words. Internal resistance, so of a cell or battery. Because again, that's where the internal resistance actually exists, and it's going to give us something to hang things on later on. So let's first of all give some idea that we know what resistance means. So is the opposition to the flow of current, if I can, oh good lord, I'm so busy talking I can't write out words properly. Right, opposition to the flow of current through the cell or battery. So again, that's already paying off that we've contextualized it. So let's go within the cell battery, through the cell or battery. It doesn't really matter what you're saying there. So, I mean, you could leave it at that, but let's add a bit more just to make sure. So in brackets, I'm going to go with causing a voltage drop across the cell slash battery. Across cell slash battery equal to current multiplied by internal resistance. So we've given some way of quantifying it and a descriptive part at the beginning. So yeah, I always find explaining what is meant by internal resistance is quite a difficult one, because people want different levels of detail on this, and it changes from mark scheme to mark schemes quite often. So putting in both things, a description and a little bit of a formula as well, it sort of covers all bases, doesn't it? Right, third part, explain why the current at X must be twice the current at Y or Z. Right, this is more or less the same as we had in the last question. So we can say parallel branches have same PD. Same PD. So we can then say, well, therefore, our I times R is going to be the same in both branches. So we can say that 6 times 0.16 has got to be equal to 12 times the current through Y and Z. So there we go. We've got high. Therefore, we can say the current through YZ is equal to half of the current through X. Right. Calculate the PD across the 6 ohm resistor. Right. Okay. Well, we know that we've got our current is equal to what were we just saying? Oh, we're working out this. So IYZ, well, it has to be half the current, so that's 0.08. So that means that our PD across the 6 ohm resistor is going to be 6 times 0.08, which is 0.48 volts, which is good. Suggest why the PD VXZ between X and Z is equal to 0. So we want the potential difference between these 2 points. Well, let's work out then that the PD across the 3 ohm resistor is equal to 3 times 0.16, which is 0.48 volts. Therefore, potential at X equals potential at Z. It's quite nice with this as well, because it gets us thinking, it's adding the context here to potential difference. As in, potential difference is the difference between in the potential from one side of the component to the other. So if we were going around the circuit saying, oh well, we've got some value of potential here, and then over here, well, we've got, for each one of these resistors, we've got a drop of 0.48 volts, then we've got a value of potential here, some value at this point, we've got some value there, and the difference between those values is the PD across the component. It's really adding the difference to our term potential difference. So we can look at any point in the circuit and assign a value of potential to it. Okay, that value of potential, it can change depending on which direction around the circuit we're deciding to analyze things, because it doesn't really matter whether we go with electron flow or current. And also what we're setting our minimum value to. Normally we say, well, it's 0 volts when we're coming back into the cell, and then the EMF when we're going back out of the cell again. So in this case, a maximum of 1.2 and a minimum of 0. But yeah, for every point in the circuit, we can assign a value of potential, and that will then tell us what will happen when we connect a wire between any 2 points. If they've got the same potential, then we're going to get no current flowing, because there is no potential difference. So yeah, it's just a nice way of thinking about it. So that's covered that. Calculate the value of the internal resistance R. Okay, well, we know that we've got 0.48 volts across, well, half of each branch. So that we know that, therefore, the terminal PD is equal to 0.96 volts. So that has to be what our terminal PD is. That means that we've got 0.24 volts across the internal resistance. So that has got to be equal to our current multiplied by the internal resistance. So what's our total current? Our total current was 0.16 plus 0.08. That's just doing Kirchhoff's first law to get our current through the cell. So that is 0.24. So internal resistance is 0.24 divided by 0.24, which is 1 ohm. Kind of fallen off the screen, so it's got a bit messy down the bottom there. But yeah, we're just working it out step by step. But yeah, you want to know, I mean, it's really useful to know what the terminal PD is. You know, if we've worked out the PD across the 3 ohm resistor or the 6 ohm resistor, you know, they're both the same. So clearly we've got the same again across that 3 ohm resistor, because PDs are divided up in proportion with resistance. So that gives us our terminal PD, gives us the PD across the internal resistance. And then we're just doing a V equals IR on the internal resistance. Right, that's a full-on question. I like that one, although the calculations are quite straightforward, but the definitions are good. I mean, really, if you struggle with being able to clearly write definitions, which I find that quite a lot of people can be, they might know what these things mean, but it can be difficult to express them in words. Having these opening contextualizations on a definition really helps. You know, it helps your understanding by saying where a PD exists or where the internal resistance exists, but it's also giving you those words that you can use, and you'll find your definitions they're so much easier to put together if you just get the start of the definition put together correctly. So yeah, I recommend keeping that in mind, which is what has made this question a really good one to go through.